Okay, next force we want to look at is force of a spring, a linear spring. And we want to calculate the work done by this force as the spring is stretched. For simplicity, let's first consider the unstretched case. Whatever length the spring has, let's take that as our reference for measuring length. And after that, from there, we want to find the force as the spring is stretched from length L1 to some length L2. So in this process, let me draw this spring again. Somewhere along the way, the force of the spring is in the opposite direction. This spring has a tensile force. And this force we know is K times L, the length. If I continue this, the momentary length L that it has. And if I want to find the amount of work done from point 1 to point 2, it is F times, let me write it in the scalar form. It was F cosine of theta ds. And in this case, force cosine of theta is always 180 degrees. Theta is 180 degrees. So cosine of theta is -1. And I can write this becomes minus force F, that is KL, times ds. In this case, ds is the same tiny length change. And that is the same as change in length L. And now we have this integral. It is on a variable L, so I can take it from L, not L naught. L1 to L2. And it is quite doable. So we know this integral is 1/2 KL squared when we want to take it from L1 to L2. And this one becomes 1/2 K L2 squared minus L1 squared. And this is the amount of work done by, where is the sign, the minus sign? This is minus. And this is the work done by the force of a spring. Again, minus sign means that because as I'm stretching, the length is increasing in some positive direction, the force is in the opposite direction. It's in the tensile direction, and that's why we have this negative sign. One other thing I wanted to mention here is if as a function of length, I draw force. As L is 0, I am at the unstretched length, I have 0 force. And my force linearly increase with length. And that is the slope of this line. And what I'm calculating is essentially the area under FL curve. And yeah, that is all I wanted to say. Is there anything else I wanted to say about force of a spring? No, not really. Oh, one other thing is here, for simplicity, I just assume spring is being stretched in one dimension. But one thing Feel free to practice it using, for instance, polar frame. Let me draw it. Oh, why is it red? This statement is valid. Doesn't matter if the spring is turning, rotating. It is all the work of spring force is always only related to its change in length. Well, squared of the length. You can see why. Come on. I don't know why iPad does this. Anyways, as the spring changes its length and direction, moving along any arbitrary path, feel free to try it as an exercise. Note that you can always write these differential vector equations in polar frame, and always your force is going to be in the radial direction, and that leads you to the same kind of equation regardless of whether your spring is being stretched just in one direction or it is actually turning. But yeah, that is how you can calculate the force, the work of a spring force. And I think that is all I have for this part. We have defined work. We have calculated work of a few forces, if the force is constant, or if it's a gravitational force, or if we have a spring force. Now, the question is, so what? We will see how we can use the concept of work alongside concept of energy to do useful deductions about the motion and how it is changing. So I'll see you in the next video when we discuss that.